Leaving off where we left off? Sure. Class 14. Yay. The steps in analyzing a flat belt drive. All right, so we're going to go through example 17.1. I don't usually use the examples in the book, but I decided to this time because this is my first time teaching this section. And I figured, I would try to get you could use this resource, and I can try to walk you through it. In fact, actually, I probably should be doing this, making videos for all of the examples in Shigley for each section, because honestly, they really do need to be explained. Sometimes they're a little bit confusing. So, as I mentioned in the previous video, the main equation, the main underlying phenomenon that's taking place is the slippage of this belt and the distribution of friction along that belt, which if you were to go to the first principles and do the integration with a free body diagram, you'd be able to see tangentially that we end up getting something where we have a relationship. I'll write it over here again. Like that's a ratio of the two belt forces is going to be E to the coefficient of friction times the wrap angle. Make sure this is in radians. Now, in this section here, we also want to account for the centrifugal forces that are taking place. So they also get played into there. But that could be considered like maybe our main equation. So in our steps, we find this from the belt geometry, and then from belt geometry and the speed, we find what the centrifugal force is going to be. The centrifugal, it's really like a tension that's being changed into the system. And then we can find from the torque, and also we have, this is a factor right here. This is a service factor that we look up from a table. And here's a design factor that we look up. And then this is RPM. I know it's confusing. They use N for both of them. But from that, we can find what the necessary torque is. From the torque, we can find what this combination of things is, right? So we're just going to treat this as like one variable first that we find. And then from tables, these two tables right here, and we'll see in the example what they tell us. We'll be able to, and from, I think from the above, we'll be able to figure out what F1A is going to be, right? And this is the allowable largest tension. So that's the allowable largest tension right there, okay? And then we'll be able to find F2 from this above, what I had said, okay? And so we just have to subtract out what we find from here, find this right from there, so that lets us get F2. And then from an earlier equation, we're able to figure out what the initial tension needs to be, right? So they need to tension the thing up. And then we're able to check what the friction would be. This is the developed friction, coefficient of friction. We want to make sure that we have a larger actual developed coefficient of friction compared to this right here. So, by the way, if you take a look at this right here, it's actually just working backwards through this right there, right? We're taking the natural log, and they're getting out the coefficient of friction. And then we find the factor of safety from the actual divided by the nominal and the service factor right in there. And kind of weird because when going through all this, you tend to get the same service factor from the beginning. But I'll try to explain all of this as we come through. Okay, so let me see. Here is I gotta see, how am I going to do this? Here is the problem itself. Okay, so here's the example. We have a polyimide A3 flat belt, 6-inch wide belt, flat belt, 6 inches wide, is used to transmit 15 horsepower under light shock conditions where KS is 1.5 and a factor of safety is equal to or greater than 1.1 is appropriate. right? Somehow we knew that. Someone gave that to us. The pulley rotational axes are parallel, right? That's good for us. And in the horizontal plane, the shafts are 8 feet apart, or 96 inches, not to scale. The 6-inch drive is a pulley rotates at 1750 RPM in such a way that the loose side is on top, right? Okay, that's good. And the driven pulley is 18 inches in diameter. And it says to see that figure. Of course, well, we just saw it. It's right there. The factor of safety is for unquantifiable exigencies. Oh, boy. Okay. Estimate the centrifugal tension, FC, and the torque. Estimate the allowable F1, F2, and Fi, and allowable power. I guess allowable power is not actual, but allowable. And estimate the factor of safety. Is it satisfactory? Okay. So some things that they gave us as part of this over to the side is the belt is actually 6 inches wide, which is kind of weird because the pulley part of the thing is 6 inches in diameter, so that's kind of a weird proportions. 15 horsepower. Here is the density of the belt. Right there, so we could look it up. There's pounds, so it's the weight density right there, and we see everything right there. All right, so it's going to be easier for me to switch the document camera for all of this. So let me switch this thing up. I'll end the show, discard, and am I going to have enough space over here? I think so. I have to move my keyboard out of the way. What a mess. Okay, I hope I didn't just screw something up by touching that. All right. So, I will use my document camera right here and get my piece of paper. Oh, that's the wrong document. That's the wrong camera, buddy. I don't need that one. I need this one. How come? Oh, that's the one that's looking up in the sky. It was working before. Oh, no. Let's see here. It says main camera. It's not going to let me do it. All right. So, is there a way to pause all of this? It was doing it before. I don't want the front-facing one. See, that's the one that's going up towards the sky. Let me do this right here. All right, well, let me pause and see if I can make this work.